of EXNL moving to EXIC and a few other changes. You'll see I've extracted bits and pieces from some of the standards to put together a presentation that just shows some of the options that are available to you. I'm also going to look at RF loop approval, because that also is becoming more of an issue as Wi-Fi and communications, etc., starting to creep into hazardous areas. So I'm sure all of you have read it. So we'll look at EXIC, Zone 2, and gas group. And then I will spend a little bit of time on some of the new technology stuff, the augmented reality in hazardous area, and just show you a quick video of the kind of things that can be done, which I think seem to be more pertinent in these days of remote working and travel restrictions, etc., etc. Anyway, let's kick off. This presentation is in a paper form. It is available on my website under the white papers for any of you that are wanting to download it. Otherwise, contact me. I'm happy to send you a PDF of the presentation and or of the paper. So let me know. First of all, just let's go back to a few basics on intrinsic safety, just to set the scene. So intrinsic safety is a system. It always it's a matter of putting the parts together. There are still a lot of people out there that believe putting a barrier or isolator in front of any device makes it IS, and it's not the case. You have to consider the full system, from the field instrument to the intrinsically safe interface, usually a barrier or isolator, and the interconnecting wiring. So basically, it's based on the fact that a spark or thermal effect will not cause ignition in the hazardous areas. So the principles of intrinsic safety, we want to limit the current, we want to limit the voltage. So what limiting the current and the voltage does is it limits the power or the energy into the hazardous area. So the way intrinsic safety performs safety is in that every gas has got a gas ignition curve of V versus I. Okay, so that tells you how much energy would ignite that gas in terms of a spark or in terms of temperature. And using intrinsic safety, by limiting the voltage of the current, you minimize the power and the energy in the hazardous area to cause ignition. The other thing that you've always got to watch is stored electrical energy. So capacitance and inductance, even though it's off. I always like telling the story of fiddling on the back of TVs. I don't know, maybe I'm getting a bit too old now, but when the TVs didn't work and that, I used to strip the back, and there were these thumping big capacitors. And even though the TV had been off for several days, if you touched across that capacitor, you could give yourself a mighty spike. So even without power applied, there is still capability of causing ignition based on the stored electrical energy. And in that, you're reading the capacitance and the inductance of the cable. Right, so if you look at the standards, they call it a DSD, which is a descriptive systems document. This is the document that details the intrinsically safe loop and does the calculations to ensure that it's safe. It's defined in IEC or SANS 60079-25 standard. In South Africa, it's most commonly referred to as an ATL approved loop, approved test laboratory. South Africa, to the best of my knowledge, is the only country that requires a third-party approval of loop typicals, something we've tried to change unsuccessfully. This gives you an example of what an IS loop drawing looks like. So you can see here the device, the transmitter in the hazardous area, and you can see its parameters. So it's suitable for gas 2C. It's certified in zone 1. It's got a temperature class of T3 and an ambient of 0 to 40. We've got a junction box here, which shows, okay, then second of all, you can see that the screens are not terminated in the hazardous area. They are fed through the junction box here. This is meant to show internal screens and the overall external screen. And this goes through to the hazardous area, out of the hazardous area to where your barrier or isolator sits, and the cable screens are terminated down to earth at that point, and then through to the control system. You can see here you've got the high quality IS earth, which is typically requires less than 1 ohm. If we look at the drawing, it's an old one that I've got, and I'm not sure that Joe Root was old enough to draw this before his time with England cricket. But this dictates the MTL part, the Rosemount field device, the PTB, the certificates that were there, the ratings, etc. And in here you can see the U0, I0, and P0, and you can see that they are lower than the UI, II, and PI. And so by this calculation, this loop approval is acceptable. You can see the capacitance, the C0 value, the capacitance inside the Rosemount flow meter, and then the two different cable lengths. And this is quite common because companies would most often run a multi-core out to the field junction box. And so it's a multi-core, shielded multi-core. And then from here, you would run individual pairs of a smaller cable. So you can see the difference in values of the cable. And again, showing the calculation of the capacitance and of the inductance to show that it's true. I'll come into this in more details. Again, let's remind ourselves of the hazardous areas and the zones. So zone 0, 1, and 2 are for gases, and zone 20, 21, and 22 are for dusts. Now, they follow exactly the same scenario where effectively the hazard is present continuously or for long periods frequently. Zone 0 for gases and vapors, zone 20 for dusts. Zone 1, it's likely to occur in normal operations occasionally. Zone 21 is exactly the same for dusts. Zone 2, it's not likely to occur in normal operation, and if it does occur, it'll persist for a short period only, and that applies to zone 22 as well. So zone 2 might be a break in a flange or some physical damage, that there's a gas leak, and the process people will know that it's happened and they'll go and fix it. So it's a fault condition on the plant for whatever reason. Okay. Again, now, how do we do the various EX ratings? So EXIA is intrinsically safe with 2 faults. Remember that 2 faults mean these are components upon which safety relies on. So in a barrier or isolator, it's a xenodiode or a resistor. So because the gas is there all the time in this scenario, or the dust for that matter, it has to be safe with 2 faults. Because it's suitable for zone 0 and 20, by definition, it's suitable for zone 1 and 2 and 21 and 22. EXIB is specified for zone 1 or 21. It now has to be intrinsically safe with 1 fault. And because it's suitable in 21 and 22, it also meets the less a requirement of zone 2 and 22. EXIC replaced the EXNL standard and is suitable for zone 2 and 22. Okay, that sets the scene a little bit for where we need to go. This is a Flamflex wall chart, which I'm happy to share with anybody as a reference guide. So you can see it tells you typically what defines a zone 0 or zone 20, which means that the hazard is there under normal conditions for greater than 1,000 hours per annum. A zone 1 or 21, zone 1 typically is like vents or sumps where the gas can be there under normal conditions, but not all the time. And that is generally designated between 10 and 1,000 hours per annum. Zone 2 is under fault conditions, which is typically less than 10 hours per annum. So that gives you a breakdown of what defines the zones. You can see that the gas and dust groups are defined here as well. It gives you a reference for IP ratings. And down here are all the various protection techniques. So flame-proof, intrinsic safety, encapsulation, pressurization, and again, whether it's suitable in gases and dusts and the zones that are done. So if you're interested in having the wall chart, please just give me a ring or drop me an email. Okay, let's have a look at how a Zener diode works. Remember now we're talking about it from a safety point of view. So under normal operation, the input voltage here would be lower than the Zener voltage, and you'd have an output here which is used to power the sensor. Under fault conditions, so say there's something wrong with your power supply or with your earth system, Vin goes above the value of the Zener diode, and now the Zener diode, this barrier is going to clamp that voltage to prevent the high energy coming into the hazardous area. So the Zener diodes clamp the voltage, the resistor limits the current. So by this arrangement, we've controlled the current and the voltage in the hazardous area. The fuse is there to protect the Zener diode. So if this voltage was here for a long time, the Zener diodes could burn out, and then the voltage will get through into the hazardous area. The fuse is there so that if this voltage is there for too long, it pops the fuse and you're still safe. The thing to note with the Zener barrier is that there's an intrinsically safe earth that is needed. So everything has to be referred back to the safe earth. So what are we talking about in how we define this? The highest open circuit voltage is the voltage of the Zener. And intrinsically safe terms, that is considered the output voltage, the maximum output voltage under fault conditions. So something in the Zener diode, in the Zener barrier has failed, and the maximum voltage you can get out here under these conditions is 28 volts. The maximum current, defined by that voltage over the value of the safety resistor, is 93 milliamps, and the maximum output is 650 milliwatts. So let's have a look how this applies to an intrinsically safe isolator. An isolator has got exactly the same energy limiting circuit here, but because of this segregation or isolation here between the safe area and hazardous area circuit, this limiting circuit is not referenced to the 0 volts to the safety earth. So it's got exactly the same parameters, but you are not reliant on the intrinsically safe high quality earth for your safety. Okay, so let's have a look at the field device and what are the parameters defined. First of all, the code is defined as EXIA, so that means it can be mounted in zone 0. It's suitable for 2C, and it has a T rating of T4. So again, the T rating is to do with the maximum surface temperature that you would see on that device, because surface temperature can also ignite a gas or a vapor or a dust. The parameters are defined as, these are the maximum parameters you can apply to me and I will still be safe. So the maximum input voltage you can apply to me is 30 volts, 100 milliamps, or 1.3 watts. And if you apply these values, I am safe. It says I've got an internal inductance of 10 microhenries and an internal capacitance of 20 nanofarads. These three parameters here define the safety description. That has to be matched to the intrinsically safe isolator, and you need to define the system. So this system is an EXIA, so zone 0. So this device, the parameters are, as I have just explained, suitable for mounting in zone 0. The barrier or isolator has got an EXIA in square brackets. Okay, the square brackets means connection to. So the barrier or isolator cannot be mounted in the hazardous area, but it can be connected to a device in this case, zone 0, and in a 2C gas group. The maximum output parameters that we saw, that we defined, are here. So all of these parameters, this is the maximum output under fault conditions. This is the maximum you can apply to me to be safe. So all of these values of the transmitter have to be higher than these three values that are the maximum output of the barrier. Okay. Now, based on the U naught value, the standards dictate that for a 2C zone 0 or 1, that you've got a maximum of 83 nanofarads, 4.2 millihenries, and an L over R, an inductance over resistance of the cable. By looking at this, the capacitance here, the 63 nanofarads, is the 83 nanofarads minus the 20 nanofarads. That gives you 63 nanofarads and allows you to calculate the cable length. Typically, 99% of the time, it's the C naught value that limits the cable length. L naught, you can see there's very little difference because it's 10 microhenries in 4.2 millihenries. And if the inductance does fail, you can always look at the L over R ratio. So the inductance can take into account the full impedance of the cable, both the inductance and the resistance. You can see here that the system is EXIA2C-T4, zone 0, 2C gas group, and a T rating of T4. I think that's around 135 degrees, which is the maximum. I'd need to double check that though. So let's have a look in a summary. So we've compared the safety parameters. We've worked out the maximum capacitance for the cable, so we can work out the cable length. And we're now looking at the system certificate, and we produce what is the ATL loop approval document, which gets signed. Okay, now let's have a look at the various gas groups. So by definition in the standards, every gas has got its own ignition curve. But what they've done is they've grouped them into groups. So all the hydrogen based, including acetylene, are 2C. Those are the easiest to ignite. Ethylene is 2B, and propane and diesel, etc. are the 2A gas groups. So the 2A are much harder to ignite than hydrogen is. So let's have a look at how this all fits together. So this is an extract from 6079-11, 2012, table A2, page 96. And what you'll see here is that the cable parameters, the C naught value, is defined by the safety voltage of the barrier, in this case 28 volts. So you can see for 2C, zone 0 or zone 1, that value was 83 nanofarads, which I showed you in my previous slide. So now if you have a look at it, the standard shows you that if you go, remember that EXIC is safety under normal conditions. So you do not need to apply the 1.5 safety factor. So if you move to zone 2 and make it an EXIC loop, you've got 272 nanofarads. Here it is on the curve. So we've eliminated the safety factor. If we move to zone 2B, we've got 650 nanofarads. And if you ever got there, 1.65 microfarads in a zone 2B situation. And the 2A values are really just academic, because when you move away from this 83 nanofarads, even to 272 nanofarads, the C naught value, this capacitance value, no longer becomes the limiting issue on your cable length. What will define your cable length is the resistance of your cable and the voltage that you will get at the end of the cable to power your transmitter. So what we have seen in the past have been two ways of getting around this. One, there was a SABS exemption, which allowed the safety parameter, the safety factor, not to be applied in 2C zone 0. That was fine. It was understandable at the time, but it's not valid. It's not a valid solution by the standards. The other way is people were using special isolators with a lower voltage, therefore a higher capacitance and longer cable. But the trade-off you have with that is you've got lower voltage, longer cable. So under operational point of view, you're not going to have as many volts at the end of the cable. And that too is a safety risk. If you've got a level transmitter that's being denied the volts it needs to report the level, that's as much a safety factor, if not a higher safety factor, than the cable capacitance. So what this shows you is that unless you've got 2C zone 0, zone 1, and you're defined by this 83 nanofarads, which will typically give you a 500 to 600 meter cable length, none of these, the kind of cable lengths that you sometimes need of 1 and 1.2 kilometers, none of the other 5 options that you have here will limit it. So this is a far slicker way of doing it. If you go back in history, people always used to just define the whole plant as zone 1, 2C. And it made sense in a way at the time because it was easy on training. Staff knew they were always in zone 1. They always knew what equipment they could use. But as people have understood the cost and the risks of doing this sort of thing, there are other options available to use. Okay, so let's have a look how we do the same calculation again. So you can see here that this is exactly the same loop approval, except that the system is EXIC. So this system, despite the fact that the field device was suitable for zone 0 and the interface can connect to zone 0, this is a system approval for zone 2. And the difference you see here is that the C0 uses the 272 nanofarads instead of the 83 nanofarads. This gives you 252 nanofarads of cable capacitance versus the 63 nanofarads that you had in the beginning. And this will not limit your cable length, as I've just explained. So this is a cable, uses the cable parameters out of the standard for a U0 of 28 volts, zone 2, 2C, and we now no longer have a limitation other than this device has to be connected in zone 2. Let's have a look at what some of the certificates say and what the implications are. So if you have a look here, you can see how the same values apply. So for an MTL 7787, here's the 83 nanofarads for 2C. Here we have the 650 nanofarads for 2B and 2.15 microfarads for 2A. Looking at the same certificate now, you can see the zone 2 parameters, i.e. where the 83 nanofarads changes to 272 nanofarads, and likewise for the other gas groups. So the product certificate on the barriers and isolators will generally indicate this for you on using it in zone 2. Here is another example that shows you the cable and inductance by gas group. So it's showing you the same thing, the 83 nanofarads, the 650 nanofarads, etc., that you're allowed to use. Something to note, though, is that in 2012, EXNL, and for those that remember, EXNL is energy limiting. By all ways of talking about it, it really was just intrinsic safety without the safety parameter. So EXNL was pulled out of the EXN standard and added into the EXI standard as EXIC. So a lot of products that were defined or designed before 2012 may not have the EXIC values on the certificate, okay, because EXIC didn't exist at the time. But the table A2 in the standards is very clear that you can use them in that way. Bearing in mind that the other part of EXNL is EXNA, which is the non-arcing standard, that is also due to be renamed as EXEC, so increased safety for zone 2. But that's not really in the scope of this discussion. So let's have a look if we want to do this for a gas group 2B. So you can see everything is the same again, except that I've designated this system certificate or this loop approval to be 2B. These parameters haven't changed, okay, because this device is still suitable for these parameters, as is the interface. But here, because it's 2B, when I do my loop approval, I've now got 650 nanofarads, giving me a cable length of 630 nanofarads. Again, the capacitance now does not define the maximum cable length on your loop. It's the functional voltage, as I said before. So these parameters come out of the certificate. These parameters come out of the standard and possibly the certificate as well. And we have a system approval for a field device in 2B, which will allow you a long cable length. There are very, very few occasions where inductance will limit your cable length, but most cables will define a number of microhenries per ohm, and because it's over a resistance, you don't lump the inductance together. So if you do run into problem with inductance, use the L/R ratio. Just to show you what a Zener barrier looks like, okay? So here you can see a DIN rail mounts. So the intrinsically safe earth connection is on the DIN rail in this example. The hazardous area fields come out from the blue side and the red side is on the safe side. Looking at it from the other angle, the DIN rail is the earth. You can see there's a little screw terminal here for the cable screens to be connected. And you've got the hazardous area connections and the safe area connections. What do isolators look like and why are they different? Well, isolators require 24 volts. There are DIN rail solutions. So basically you would put 24 volts on the side. You connect to your hazardous area from here and to your safe area from the gray terminals. But remember that you don't need that intrinsically safe earth for safety. It's still you still need to use the high quality earth to screen your cables, just so that your analog values are not noisy. If you've got large amounts of I/O like you have at various of the petrochemical sites, you can backplane mount it, and there are options here for connection to various control systems, and this allows for redundant power. These are diode ORed to give you redundant power. Worth noting too that you can do multiple channels on the isolators as well, which does make them more cost effective. This is the new isolators that are coming out. So everything is moving towards this universal. I must admit, I'm still a little bit old school. I still think we should be doing our homework before we're buying hardware. But given the times pressures we are under these days, I kind of understand. And a number of vendors have come out with a smart solution. So if you look at this product, here is the field terminal. So this is a field terminal only. You can see that the gray bit here, this is the galvanic isolator. And at the time of FAT, you can choose whether that's digital in, digital out, analog in, analog out. So you can buy all of this hardware up front, and then if your analog changes to a digital, you're not worried about returning and buying new isolators. So it is quite slick from that point of view. The other things that this gives you is that there's a loop disconnect on the field terminal itself. And as you can see here, if you want to, you can just clip surge protection onto the field terminal itself. So what this is doing is where we would traditionally have had anywhere between 3 to 5 racks in the marshalling, terminating on the field terminal, cross-patching, surge protection, galvanic isolator to the control system. You can get all of that functionality in one setup. There is a demo system of this running at the Honeywell hub in Secunda. So again, it is very slick. It's a more expensive solution, and a number of vendors are coming out with similar kind of products. This gives you a slightly different way of looking at loop approvals. So here we are multi-dropping devices in the field. So this is a temperature multiplexer system. So you can have 16 RTDs or thermocouples in the hazardous area. You can parallel up the transmitters. So you've got 2 transmitters, and then 32 inputs over a single cable connection. We've got a galvanic isolator here, which uses the U0, which defines the U0, I0, and P0. And then these transmitters connected in parallel have got a UI, II, and PI. The whole part of the loop approval still looks exactly the same. It's just that you've multi-dropped field devices in the field. Everything else applies. This is the receiver. So this powers the transmitter, similar to a 2-wire 4-to-20. And there is a data communication back to the receiver, which can then be connected via RS485 or Modbus Ethernet back to a control system. So this has got some mileage if you consider some of the LEPIU systems that are probably beyond their useful life in South Africa at the moment. All right, that kind of concludes the gas group, the zoning, the various types of designating how a loop is certified. The next thing that comes up is that RF, radio frequency, Wi-Fi in hazardous areas is starting to become a big thing for many reasons. And just to set some context, these are EXD enclosures, the blue ones. This is for mining, so for underground coal mines. This one is for the petrochemical industry. And inside here has got a Cisco access point or an Aruba access point. And this gives you a Wi-Fi that can be mounted in zone 1. This is an extruded aluminium version of it. It's a lot more flexible, and this can be mounted in zone 2. So how do we do a loop approval given that the antenna here is intrinsically safe? There are 3 items that come into it. First of all, we've got a galvanic isolator for RF. You can see here that this isolator is certified EXNA, so it's non-arcing, so it can be mounted in zone 2, but it's got connections to EXIAGA, so zone 0, so the antenna can go in zone 0. It's suitable for a 2C gas group, T6. And for zone 2, EXIC, with a connection to zone 0 for dusts. Here's your mining, where this galvanic isolator allows connection into a zone 0 in an underground coal mining situation. These are just coupling devices. Obviously, you've got an access point inside a metal enclosure. It's not much good to anybody. You can take the antennas out from the cable glands, or alternatively, this is a little EXD transit connector, which allows you to take the antenna. The advantage of this is that you don't really need a certified antenna. Certified antennas are quite limited in their function if you buy flameproof, their size, their distribution of the Wi-Fi. Whereas by using this, you've got flexibility to use any antenna that you require. Obviously, you still need to do an analysis for static, for example, to make sure that it's not going to have a static risk. But now by using a different antenna, you've got flexibility on using other manufacturers' antennas to get directional Wi-Fi, etc. So let's have a look at how the loop approvals work and how the standards apply. First of all, what do the standards say? The standards say that in group 1, underground coal mining, you can transmit 6 watts. Okay. In gas group 2C, you're limited to 2 watts. Okay, and you can see all the values here. Now, for Wi-Fi in particular, all of these values are rather meaningless in the fact that most access points only transmit 100 milliwatts. So we are well under these wattages. To remind you that that radio frequency can induce currents in metal structures. And obviously, if there's currents flowing in metal structures, you can still get a spark. And that's what these threshold powers are there to define. Things to note, though, is that although the 6079 standard limits you to 6 watts RF, the DMR issued a directive in 2003 that limits you to 500 milliwatts for Group 1. This has been a bugbear for a long time, and frankly, our legislation is not in a sound state at the moment. But anyway, there's this directive in 2003 that, in my opinion, is well outdated for the technology that we're currently using. It was reissued in 2010, but it was never actually signed by the inspectorate. And nor has this requirement been brought into the later versions of the ARP. Right, let's have a look at the loop approval. So the first one I'm going to do is an underground coal mine. You can see that by EXIA-MA, so it's Zone 0, Group 1. We've got an antenna here, which can be mounted in Zone 0, Group 1. What have you had to watch? You've got to watch static. You've also got to watch the fact that there's no aluminium, because in an underground coal mine, you've got a damp situation and you can get rust.
Also, not the people said no, the insurance you pay because it's such pre-existing condition.
Okay, so we've got the antenna is defined as a simple apparatus device. So and there's no DC parameters associated with it. No UI, no II, no PI. We don't need to show that EXD transit because it's not part of the loop approval, but you can see the galvanic isolator. Looking at the galvanic isolator in the same way that we showed the manufacturer and the model and the IA certificate, you can see the EX rating. But now what's important is that we need to do the RF approval. So what we've done here is you can see that although it says that you allowed 6 watts in the standards, the DMR states 500 milliwatts. So you need to be very careful in the selection of the gain of your antenna. But to get from 100 milliwatts up to even 500 milliwatts, that's obviously quite a high gain antenna. And to be honest with you, with the directional antennas, we are experiencing distances of up to 1 kilometer in some coal mines where the shafts are relatively straight. You can see here that we've done the work, and MTEX, one of the ATLs, has signed off on the loop approval. And you can see here that we have included very specifically the antennas that are certified or suitable to be used. And we also worked with Pointing to put some of their antennas in here based on the requirement from a particular end user in South Africa. So we specify here the difference between what the standards say and what the directive from the DMR says is 500 milliwatts. But you'll notice that because there's no DC, there's no UI, U0, etc. parameters. You've only got an RF consideration and a designation of the antenna. Let's look at it from a Group 2 or a Group C version. Okay, the antenna is exactly the same, but we've got a 2C or 3C group, a temperature class rating, and a maximum ambient temperature. We've got the galvanic isolator in the same way. You can see it's basically telling you you can use any antenna as long as it meets the static requirements. It's a simple device, no parameters. And if you have a look at the certification of the isolator, that's shown here. And as per the standards, 2C is 2 watts, 2B is 3.5 watts, 2A is 6 watts, 3C is 6 watts. So when you design the gain, or when you select your antenna to choose the gain, you've got to make sure that the 100 milliwatts put out by the access point is not above these threshold values. And again, this is a loop approval signed by by an ATL in South Africa for a specific end user. Why do you want Wi-Fi? All the mobile devices that are available, certified for underground coal mining, for petrochemicals, so you can be walking around on the plant, and with the way VoIP works these days, you can be answering your phone as though you're sitting at your desk in much the same way as I'm talking to you today. There's a little Android headset which can be used for augmented reality, and I'll explain to you how that, I'll give you a demonstration for remote assistance. This is a software package called Utility AR, but there are many others. You can use Teams, you can use even use WhatsApp for that matter, Skype. And what does remote eyes or augmented reality give you? Remote eyes, real-time data, and all the data that you can extract. These devices are certified for hazardous areas, and they are a voice-activated Android phone in their own right. So what I'm going to try and do now is switch through to a video to show you how this functions. Okay, so this is a remote advisor. So given the days where we're at now, where nobody can go to site, it's difficult. You've got a guy in the field wearing a headset with smart glasses. You've got a guy sitting 3,000, 10,000 kilometers away who can see exactly what this guy is seeing from the camera on his headset. He can draw, annotate, direct the guy, tell him what to do, look at the cable wiring, etc. So in the days where, you had a field expert because you bought the equipment in Canada or Germany, you can't fly, you don't need to fly the guy into the country and take him on site to be able to fix the problem. So this software really allows you, or this technology allows you to direct somebody on site to sort out the problems. For any of you that have been underground in a coal mine, I mean, it's a nightmare scenario in a way, because just to get the security clearance to go underground is a bit of a mission. So you've got to drive to the mine, you've got to get all your security, then you've got to gear up. For me, I went about 180 meters underground, and then you get into a modified vehicle and drive for 5 kilometers in a very uncomfortable situation to go to the distribution box that you need to be able to see. Okay, so this and all of this, you've spent a whole day, and there's all the security, all the risks of having visitors. Often these people are overseas visitors, and their security is an issue. This is a really easy way of getting your expert on site to work with somebody that's already working in that environment, and we can have a phone call this afternoon and do this setup tomorrow. This augmented reality and remote support, etc., is an amazing development in technology from the days when we used to sort of take over people's PCs with things like the early versions of TeamViewer, etc. So you can see how this guy is being directed by somebody sitting miles away and telling him what to do, how to get it to all operate. All right. So if I now try and find my way back to the presentation. Okay. Again, the video is available on the website, and the information for anybody interested. What else does Wi-Fi give you? For those of you that have been on site when there's been either a real emergency or whether there's been a practice, obviously it's always a nightmare. It takes 4 hours to clear. Everybody gathers at specific points. We're all queuing with our passes to swipe our passes to say we're present in the area. And again, a new technology. This device is a Wi-Fi RFID device, so you can track where everybody is dynamically. So not only do you know that people are there, you can actually know where somebody is. These devices also give you man down. So say somebody's on site and they fall, you can go and get that message back to the control room. And somebody can be sitting again thousands of kilometers away looking where everybody is. So when you do mustering or evacuation, you're not waiting for 4 hours to be cleared. You can see immediately whether anybody is still left on site, where anybody is in trouble, And these devices have got a press button, so you can actually call for help if you need it. This device is now being used as GPS as well. So whereas this needs a Wi-Fi distribution to triangulate location, these devices can use as GPS and refers it back. There's further development using BLE, so Bluetooth, low energy, and using other technologies, LTE, for example, to eliminate the need for Wi-Fi. The other products are just for RFID tracking for in stores when you're looking for devices, or you're looking for things in your stores. You've got a little RFID reader and you can find your stock. If you'll allow me just some information on some products, some new products, X-Tech have signed up with Sensia. These are active noise reduction headsets with peer-to-peer two-way radio communication. So obviously in noisy environments, and again, if you think of COVID, where you're trying to talk to somebody and you're getting 2 inches from their face and shouting at them to get your message across, these headsets can be used as two-way radios. They will actively reduce the ambient noise that is around, and these can be grouped into frequencies. So you can have teams on site of 6, 8, 10 people all on the same frequency, and you can have other teams around who are working on a different frequency and are able to communicate. Again, with all the parameters for communication. These do have Bluetooth, so if you wanted to connect it to a phone or a tablet, you could do that. A camera that is available that we're seeing a lot more use of for doing inspections or for signing off documents, etc., taking photographs in hazardous areas. A different tablet that we've got for Windows, for those people that require Windows tablets, and the displays and indicators that we've been selling since the 1970s. Right, everybody. I mean, that really is completes the presentation. I'm happy to answer any questions or address any issues that anybody has. Are there any questions?
I don't see any questions in the chat box.
Hi, Gary. Dave Lincoln, yeah?
Hi, Dave.
How are you?
How are you doing?
Very well.
Good.
I signed in a little bit late, but that's not a problem. You talked about these devices underground that talk to Wi-Fi.
Yeah.
Obviously, the Wi-Fi has to be, if you want to call it, generally available underground.
Correct.
You're not supplying the Wi-Fi.
No, we do. We do supply the Wi-Fi. You must remember that in standard mines, other than coal mining, there's generally no hazardous areas.
Yes.
So under those circumstances, you can put just rugged Wi-Fi down, in which case I would not have any involvement. But these access points here that you can see on my screen, these are certified for underground coal mining. Yeah. So what we've done is that they've run rugged access points down the shafts, but then in the hazardous area and the 180 meters from the rock face, you can mount these EXD enclosures which sit on a fiber optic ring. Yes, and then that gives you Wi-Fi. So that allows you to use your phones and tablets as phones, as two-way radios. It allows you access to the internet for all your design documentation. And if you use the tagging and tracking and you carry the tags, which is what most of the mines are busy looking at the moment, is personnel tracking and safety, using those tags to know where people are, so that in the event of an accident, you can locate all your people.
The problem we had was to get the Wi-Fi to go around the corner, because what they had, when I worked at Madikwa, they were looking at vehicle management, And they were going to use Wi-Fi for that, but you got to get the Wi-Fi to go around the corner, and that was the problem.
Well, you can see here that these antennas are mounted on top of the enclosure, but there's nothing wrong with you taking cables. And so what we've done is you can mount this somewhere. You can run 2 antenna on the enclosure and go around the corner and mount just the antenna.
Okay. So on a bend or something, you'd have to mount one of these aerial clever devices so it can go around the corner.
Yeah, well, you just need to mount. It's obviously the transmission is where the antenna is.
Yeah. Okay. All right. Thanks, Gary.
Or alternatively, you mount the access points at your junctions on your in your shafting system as well. So if you mount them in the junctions, it'll obviously go down the tunnels in 2 dimensions. And
you also mentioned that being on fiber, we also introduced blown fibers down in the mine, and that worked like a dream, eh?
Yeah.
You can add.
Well, the problem is that if you hop from access point to access point, you halve the bandwidth with every hop. So what we've looked at doing is we've had a fiber ring. So right from where you come down the shaft all the way down the tunnels, you have every, I don't know, depending on what sort of accuracy and bandwidth, say every 500 meters, you would have an access point with a fiber connection to the last 180 meters, and your fiber returned back to the shaft. Then any access points that you've got while you're having to move while the wall moves as you operate, obviously your area moves so much every week. But the devices that you've got, they can hop on or bridge to the network, and then when the rock face that you're mining has moved by 100 meters, you just wire up your next access point, extend the fiber, and then you're in your area again. We've also worked with the continuous miner people to mount using the same technology to put access points into vehicles. So some of the trolleys and some of the continuous miner and shuttle cars, etc., you can mount an access point on, and they move. So again, it'll give you Wi-Fi distribution, the best you can get in terms of, and it's just a matter of cost.
Sure.
I say just.
Thanks. Go well, eh?
Yeah, keep well, Dave. Nice to hear from you.
Gary, Pullen Govender has a question, or he's raised his hand.
Hello.
Hi, Pullen.
Hi, Gary. Good evening, Gary. It's Pullen Govender from Engine Refinery here. So, Gary, I just want to find out which organizations are legally certified to carry out zone classifications in the plants, and to whom are they accountable?
That's a good question, because it's not really that clear, to be quite honest with you. I mean, obviously the ATLs, so the Explo Labs, the MASC, MTEX, SAILab, SABs, those guys are obviously are done, but there are a number of specialist MIE companies out there that specialize in hazardous areas. To the best of my knowledge, I don't believe there's anything that stops any of us doing it per se, but obviously it comes down to your definition of a competent person. So, and what we've done within the Flameproof Association is we've set up over the last 5 years a huge network to try and train MIEs. So your master instrument electricians that you have that are able to do these sorts of things, I would always check that they've got some hazardous area experience, or, you know, they've got COMPEX training or the IECEX equivalent of it, and the training is coming out of it. You really need to select your MIE very, very carefully if you're going to do it. And you would have your own HAZOP and your own people that would sign off on it.
Yeah, thank you, Gary. And are they, or do they need to be registered with, or maybe the Department of Trade and Industry or anything like that?
Not that I'm aware of. That really gets, not that I know of, but I mean, really, companies like Engine or Sasol or that, we should really take people on their pedigree. You know, you wouldn't go looking for the local street mechanic to work on your Mercedes.
Okay, thank you very much, Gary.
Pleasure.
Gary, Naveen Singh has just said, hi, Gary. Naveen Singh here, ex-SAPREF and Engine, now Saudi Amarak, Aramco in Saudi Arabia. This new virtual meeting is brilliant for us members living abroad and allows us to keep up to date with industry trends and benefit from the SAIMC.
Hi, Naveen. Good to hear from you. Really nice to hear from you. You've been in Saudi Aramco for a while now.
Yeah, six years I'm here. And I miss out all of these meetings, and they do not expose us to much technology here. It's kind of more take from us than give us anything. So now with this new virtual meeting, it actually allows us to keep up to date. This is brilliant.
I must say, I've got a lot of contact with a lot of the ex-Chevron, Jacobs guys, all of them that have gone to various parts of the world, the Middle East in particular. It's it's interesting how these. It's something for the SAIMC to consider, how we do a mix of a face-to-face meeting, but also transmitted, because I do think there's a real value in
100%.
For people that can't travel. I mean, even from one end of Joburg to the other.
It is something that we are looking at doing going forward.
Yeah,
as a
it makes
branch.
sense. Makes absolute sense.
Are there any more questions for Gary? Okay. Then I'd just like to thank you, Gary. Thank you very much for a very good presentation. Really enjoyed it. It was one I've been looking forward to. And yes, we look forward to seeing everybody in the future at the next meeting.
Thanks very much, Dean.
I also
For
would like to
anybody
say,
that wants the wall charts or the presentation or the paper, please drop us an email or give me a ring.
hi Gary, nice to see you, and thank you very much, man.
Pleasure. Thanks very much, Johan.
Gary, before you go, what email or for the presentation? How do we get around that?
Gary@xtech.co.za or sales@xtech.co.za.
If you would like a copy of the meeting, we've got a video recording of the meeting as well that you can just drop Anne or myself an email.
Okay, I'll speak to Miss Anne.
Cool.
Yeah, you know you've got my cell phone number and my email address here. They haven't changed.
Okay, but you're not here now, eh?
No, but my phone, I answer my phone all the time. It redirects via VoIP. So I'm still working. I'm just sitting here.
No problem. I'll talk to Miss Anne.
I was coming out every 5 or 6 weeks before COVID to see everybody, and I was due to fly next week, but I'll come as soon as circumstances allow. I'll be back there and give you a shout.
Thanks, Gary.
All right. Cheers, all.
Cheerio.
Cheers, Gary. Thank you very much.
Thanks, Ab. Cheers.
Thank you for joining us.
Thank you
Thanks,
very
guys.
much.
Cheers.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.
Thanks, Gary. Bye.